In last section, we introduced basic concepts of deep learning, and in this session, we focus on how to use deep learning models for medical image segmentation. Usually, in the medical image segmentation applications, we use architecture called fully convolutional neural network, to deal with the segmentation task. So, what is a fully convolutional neural network? What is the difference between the fully convolutional neural network and the traditional convolutional neural network? Actually, compared with traditional CNN, the FCN, fully convolutional neural networks, has two features. First, the FCN upsample the feature maps by interpolation. As mentioned, in traditional convolutional networks, the pooling operation, do great downsampling of the feature maps by merging relatively smaller feature maps into larger one, to reduce parameters and computational cost. It is enough for cause detection and classification task, but it is not enough for pixel-wise segmentation task. In such a case, we have to upsample the small feature maps to the one with larger resolution, to make pixel-wise prediction. So remember, the first feature of FCN is we have to upsample the feature maps by interpolation. Second, we replace the original fully connected layer with common convolutional layer so that we can input arbitrary size of input image and output the predictions, the results with the same resolution of the input image, so that we can have pixel-wise results, segmentation results. So remember the two features of fully convolutional network. First, we upsample the feature maps by interpolation. Second, we replace the fully connected layer, with common convolutional layer. So next, we introduce some deep learning models proposed by our group to deal with some challenging medical image segmentation tasks. The first application is liver segmentation from 3D CT images. Liver segmentation from 3D CT images. It is a very challenging task due to the following reasons. First, the contrast between the liver and adjacent organs is relatively low, so it's quite difficult to distinguish the boundary of the liver, with the adjacent organs. Second, the existence of various pathologies, such as tumors and cirrhosis, make this task even harder. In addition, there is a large variation of inter-patient shape as well as intra-patient shape in different slides and angles. So these figures show the challenges, of this task, liver segmentation from 3D CT images. You can see the liver exhibits relatively large, variation of shape and appearance, from different slides and angles, exhibits very large variation. So it's quite difficult to develop an automatic segmentation algorithm to deal with this scenarios. In addition, in the figure 3, you can see the pathologies such as tumor and cirrhosis. So in figure 3, there is a tumor. Make this task even harder. So we propose a novel deep learning model to handle this challenging task. So this figure shows the network architecture of our model. Okay, so our model, okay, is based on fully convolutional neural network, and it has several important features. So first, it is an end-to-end 3D fully convolutional architecture. Okay, as I mentioned, in natural image processing, okay, most images are 2D images. So before our work, okay, most FCN architectures are 2D neural networks, okay, but we propose a 3D fully convolutional architecture to deal with the liver segmentation task from 3D city images. Compared with 2D network, the 3D network can take full advantage of 3D spatial information to achieve more accurate segmentation results. In addition, as mentioned, we develop a lot of deconvolutional layers to upsample the feature maps by interpolation to achieve the pixel level segmentation results. More importantly, we introduce a mechanism called deep supervision in the learning process. Okay, that is, we use an overall objective function to let the results of the higher layers in the network to guide the training and learning of the early layers. That is, to construct some interactions between the higher layers and the early layers. Okay, use the results of higher layers to guide the training and learning of early layers, okay, during the training procedure. Finally, we also propose a CRF technique to refine the segmentation results by refining the contour. Okay, so this figure shows some segmentation results. Okay, you can see in each figure there are two kinds of lines, red lines and green lines. I forget, okay, which one represent our results and which one represent the ground truth. Anyway, okay, one of them represent our results, our automated segmentation results, and the other one represent the ground truth. But you can see from these figures, okay, in different scenarios, in different things, okay, our automated segmentation results are quite consistent with the ground truth, okay, demonstrating the effectiveness of the proposed model. So these two tables, okay, listed some quantitative results, okay, based on different evaluation measures, okay, you can see that our methods, okay, achieve relatively good results compared with state-of-the-art results. And particularly, we achieve these results with a much faster speed compared with traditional results. Okay, these figures also demonstrate the advantages of our model compared with traditional models. Okay, the second application is prostate segmentation. Segment prostate from 3D MR images. It is also a very challenging task, okay, for the following reasons. First, different MR images have global inter-scan variability and intra-scan intensity variation due to different MR scanning protocols. Second, okay, in many MR images, okay, there is a lack of clear boundaries due to the similar appearance of the prostate and surrounding tissues. So it's quite difficult to distinguish the boundary between the prostate and the surrounding tissues. In addition, prostate has a wide variation in size and shape among different subjects. So this figure, okay, shows the challenges in this task. You can see in different MR images, the shape, size, and appearance of a prostate is quite different. So it's quite difficult to develop an automated segmentation algorithm to comprehensively deal with all these cases. Quite difficult, okay? There is another challenge, okay, for using deep learning in 3D prostate applications. Okay, actually, one of the main challenges of using deep learning models for medical image processing application is that the limited training data, okay, compared with natural image processing tasks. Because in natural image processing tasks, we usually can collect a large number of training data to train a model, okay? But in medical domain, quite difficult for us to collect a large number of training data for a specific task. Okay, for example, in this application, quite difficult for us to collect a very large number of 3D prostate MR images. It's not an easy task. So one of the challenges for using deep learning in 3D prostate application is how to train an effective model and limited training data. So we propose a set of strategies to meet this challenge. First, we propose a set of data augmentation methods to enlarge the training data set, data augmentation. Second, we propose a technique called skip connection to boost the information propagation in the network, okay? To dig the potential of the training data to improve the performance of the training, okay, and the model, okay. Showing this figure of residual connections between different layers, okay. It is a kind of skip connection, okay. The skip connection can address the degradation problem and can also accelerate its convergence and improve performance, okay, during the training. Particularly, we introduce mixed residual connections in our network. Okay, there are some short residual connections, and also there are some long residual connections. Okay, long residual connections. The long residual connection connect the corresponding residual blocks with the same resolution in the down sampling path and the up sampling path. Okay, connected the features, okay, with same resolution in the down sampling path and the up sampling path, so that, okay, the results in the up sampling path, okay, layers can get the training of the layers in the down sampling path, okay, and the down layers in down sampling path can transmit the spatial location information to the layers in up sampling path. On the other hand, the layers in up sampling path can transduce gradient flow back forward to the layers in down sampling path. Okay, in other words, okay, there are complementary information between the layers in down sampling path and up sampling path, so that we can take advantage of this complementary information, okay, to accelerate the convergence and improve the performance of the proposed model, and in such a case, okay, improve the segmentation results. Here are some results of our model on prostate segmentation. Okay, there are still two kinds of lines, the red color lines and the yellow color lines. Okay, one of them represent the ground truth, okay, labeled by doctors, and the other color represent our results. You can see that in most cases, our results, our automated segmentation results are well consistent with the ground truth labeled by doctors, okay? In some cases, there are some difference between the ground truth and our automated segmentation results. But you can see that in most cases, in most part of the boundaries, the results, automated segmentation results and the ground truth are quite consistent. Okay, somehow demonstrate the effectiveness of the proposed deep learning model in the prostate segmentation from MR images. Okay, so this two table, okay, show some quantitative results. Okay, actually, our methods achieve the first place. Okay, rank the first place. Okay, in a challenge, international challenge. Okay, so you can see in most measures, our model, okay, achieve the best, okay, results, okay, compared with state-of-the-art methods, okay, demonstrate the effectiveness of the proposed model. So next, we briefly introduce another important application, brain image segmentation from 3D MR images. Okay, we proposed a multimodality, okay, learning architecture, okay, to segment important brain tissues from 3D MR images. Okay, this figure shows the network architecture. Okay, actually in this network, we take advantage of the complementary information of different MR imaging modalities, okay, to carry out this challenging segmentation task. Particularly here are the results. We rank the first place in a very famous challenge out of 37 teams around the world. Okay, it's a very remarkable achievement. Okay, it's very a challenging task, and there are a lot of very good competitors. Okay, so this is a very remarkable achievement. We rank the first in this famous brain image segmentation challenge. Actually, in recent years, we have participated a lot of challenges, medical image processing challenges. Okay, actually, we totally we achieve around 16. Okay, uh, we achieve rank first in around 16 famous challenges in medical image processing tasks. Okay, demonstrate that in recent years our group have developed a lot of efficient and robust deep learning models. Okay, to handle various medical image processing tasks. And in the future, we will further study how to make these models more accurate, more efficient, and more robust. Okay. Anyway, okay, from these examples, you can see the deep learning models are very powerful tools, particularly in medical image processing. And if you are interested in this topic as well as interested in AI technology, you can read more papers on this direction. Okay, it's a very important direction in healthcare innovation. Okay, using advanced deep learning model in medical image processing tasks. Okay, at the end of this lecture, okay, I will remind you of some important issues. Okay, as I mentioned at the beginning of this lecture. Okay, I will emphasize these issues again at the end of this lecture. First, okay, notice that the deadline of the first presentation is approaching. It is tomorrow, March 31. Okay, you should submit your presentation file with voice presentation. Okay, before 11:59 p.m. Okay, by tomorrow. Okay, please upload the file with voice presentation in YouTube, okay, or send it to me by email, okay, but it's better to upload it to YouTube because in sometimes the file, the size of the file is very large, okay, exceeds the capacity limitation of email, okay. Importantly, okay, please keep it available at least to July 31 to facilitate the marking procedure. In addition, please notice that we shall replace the face-to-face written test with an individual reflection report because the university strongly suggested we cancel the coming face-to-face activities. So we have to cancel the face-to-face written test. The specification of the report, okay, and maybe probably a template of the report will be released soon. Okay, so thank you for listening. Okay, remember, submit your first presentation by tomorrow. Okay, thank you.